Computers are revolutionizing our lives, performing tasks unimaginable only decades ago. This was made possible by a long series of innovations, but there's one foundational invention that almost everything else relies upon: the transistor. So what is that? And how does such a device enable all the amazing things computers can do? Well, at their core, all computers are just what the name implies: machines that perform mathematical operations. The earliest computers were manual counting devices like the abacus, while later ones used mechanical parts. What made them computers was having a way to represent numbers and a system for manipulating them. Electronic computers work the same way, but instead of physical arrangements, the numbers are represented by electric voltages. Most such computers use a type of math called Boolean logic that has only two possible values, the logical conditions true and false, denoted by binary digits 1 and 0. They are represented by high and low voltages. Equations are implemented via logic gate circuits that produce an output of 1 or 0 based on whether the inputs satisfy a certain logical statement. These circuits perform three fundamental logical operations: conjunction, disjunction, and negation. The way conjunction works is an AND gate provides a high voltage output only if it receives two high voltage inputs, and the other gates work by similar principles. Circuits can be combined to perform complex operations like addition and subtraction, and computer programs consist of instructions for electronically performing these operations. This kind of system needs a reliable and accurate method for controlling electric current. Early electronic computers like the ENIAC used a device called the vacuum tube. Its early form, the diode, consisted of two electrodes in an evacuated glass container. Applying a voltage to the cathode makes it heat up and release electrons. If the anode is at a slightly higher positive potential, the electrons are attracted to it, completing the circuit. This unidirectional current flow could be controlled by varying the voltage to the cathode, which makes it release more or less electrons. The next stage was the triode, which uses a third electrode called the grid. This is a wire screen between the cathode and anode through which electrons could pass. Varying its voltage makes it either repel or attract the electrons emitted by the cathode, thus enabling fast current switching. The ability to amplify signals also made the triode crucial for radio and long-distance communication. But despite these advancements, vacuum tubes were unreliable and bulky. With 18,000 triodes, ENIAC was nearly the size of a tennis court and weighed 30 tons. Tubes failed every other day, and in 1 hour, it consumed the amount of electricity used by 15 homes in a day. The solution was the transistor. Instead of electrodes, it uses a semiconductor like silicon, treated with different elements to create an electron-emitting N-type and an electron-absorbing P-type. These are arranged in three alternating layers with a terminal at each: the emitter, the base, and the collector. In this typical NPN transistor, due to certain phenomena at the PN interface, a special region called a PN junction forms between the emitter and base. It only conducts electricity when a voltage exceeding a certain threshold is applied. Otherwise, it remains switched off. In this way, small variations in the input voltage can be used to quickly switch between high and low output currents. The advantage of the transistor lies in its efficiency and compactness. Because they don't require heating, they're more durable and use less power. ENIAC's functionality can now be surpassed by a single fingernail-sized microchip containing billions of transistors. At trillions of calculations per second, today's computers may seem like they're performing miracles. But underneath it all, each individual operation is still as simple as the flick of a switch.